All right, physics lesson 3.3, graphing position with changing velocity. Okay, dog pulling a dog and Roman. Okay, anyways, so how this is going to work. So before we were able to graph our position because our velocity was constant. So if our velocity was 3 meters per second, then our position changed by 3 meters every second. So 3 meters, 6 meters, 9 meters. When you get to 3.2, homework, that's like the first question is, how does the position change? But now we are introducing this changing velocity. So our position time graphs are going to look a little bit different. They're going to have this parabola shape here. It's going to be a curve. And the type of curve that it has depends on our acceleration. So even though we've been graphing velocity over time, now we can look at how our position changes with this changing velocity. So let's look at a couple of scenarios here. First one, velocity is constant. And this happens to be at 0, so our position stays exactly the same. Velocity constant at 0. This one, we have a constant velocity, but now we're positive, so we have it going up. And then here we have constant velocity, but negative. Now, our velocity is no longer constant. We have it accelerating. So our position is going to change. Our position graphs are going to change. Basically, if you think about it like this, before, our motion maps look like this, where all the arrows were the same. Now, our arrows are going to get bigger because we're able to cover more distance given the same amount of time, because we are essentially having a change in velocity, right? All right, so quick practice. So here we have a couple of different graphs, and I want you to identify whether or not they are positive, negative, or no acceleration. So these are all position time graphs. We're not doing anything with numbers yet. We'll save that for the next section. I just want you to be able to look at the graph and kind of get an idea or feel of how they look. So here, our position is changing as time goes on. It looks like our position is getting greater and greater. So hopefully you're able to identify that as, thought it froze for a second, positive. Then we have over here, we have our position changing, and it looks like it's at a constant slope. So that probably means that we have no acceleration at all. If there's no curve to it, that means that our velocity is remaining constant. That means we can calculate the slope. It's not changing at all. Here, our slope is changing. Here we are having a position. We started off far, and then we're getting less and less. So hopefully that is negative. Now this last one's a little bit tricky. So here what we have is something similar to if you're rolling backwards or if you're falling downwards. So yes, the acceleration is negative, but it's important to note that the distance and the speed are increasing. So you're getting farther away from where you started from, and you're doing so at a faster speed. Now the velocity is negative, but the speed is increasing. So think of it like this. If you were to, I don't know, suddenly throw your cell phone out the window. I don't know why you would do that, but if you did and you threw your cell phone out the window, well, what would happen? Your cell phone would start to increase its speed as it went down. It would speed up. It would speed up because of the pull of Earth, and then it eventually go and hit the ground, probably shatter unless you have one of those crazy life-proof cases. Then, the case would break instead because that's what you pay for. I don't know what happens with those things. But anyways, that's what you're going to try to think about it. So just because you have a negative acceleration doesn't mean that you are slowing down. Just because gravity is negative does not mean that you're going to slow down and just have a nice glide down. All right, move on a little bit more. Okay, so that's it for 3.3, and I'll continue with 3.4 in just a little bit.